Welcome to Ask and Learn.
So the first question is saying, what's the relationship between spontaneity and speed of reaction? And this really important thing to know is that a spontaneous reaction is governed by values like delta G naught of a reaction or K, the equilibrium constant, but the speed is governed by lowercase k, not that you can really tell, but lowercase k, the kinetics, the kinetic rate constant. And so these two things are completely unrelated. An example, so like just because something is a spontaneous reaction doesn't mean that it's fast. A firework exploding, that's spontaneous once it gets over the activation energy, but it's really fast. But iron rusting is also spontaneous, but it's nowhere as fast. And so there's no relationship between these two. Second question is about whether something going from reactants to products is spontaneous. What about the reverse reaction? So the simple answer is that yes, the reverse reaction will be non-spontaneous. And you think about it like just sort of obviously where, okay, if going this way is natural, the other way is going to be unnatural. But the mathematical way of thinking about this is, so if this is spontaneous, the k value for this is greater than 1. And when you reverse a reaction, you take the k of the reverse is 1 over the k of the forward. And so if this was greater than 1, the reverse reaction would be less than 1, which means non-spontaneous. Now this one that you have to be careful with. So delta G equals delta H minus T delta S. This is our definition of Gibbs free energy that relates enthalpy and entropy. And so it says, what if do all of these reactions where they're spontaneous, in other words, delta G is negative, is delta H negative? And often it is, because that helps make delta G negative. But we could have delta H be positive, and if T delta S is enough positive as itself because it gets subtracted, in other words, if the entropy is positive, this will be a negative value overall, including the minus sign, and then we could have delta G still be negative. And so, in other words, even if delta H is positive, which to say it absorbs heat, if the entropy is positive, there's more disorder in the system, that means we can still have delta G be negative at high enough temperatures. An example of this is dissolving sodium chloride, NaCl, in water has a delta H that's positive, but the reason it's spontaneous, and you would know that because you can put salt in your water, is that the entropy increases. And so there are examples where delta H is positive and heat isn't released, but it's still a spontaneous process. What about taking water from a liquid to being a gas at 100 degrees Celsius and 1 atmosphere? Well, this is exactly the boiling point of water. And so this is one where there's a little bit of a catch here. There's sort of three different situations that can happen. If delta G is greater than 0, it's non-spontaneous. If delta G is less than 0, it's spontaneous. If delta G is equal to 0, it is at equilibrium. And this is the one that we often forget because it's less common. But in this case, where we're exactly at the boiling point, we're at a perfect equilibrium between liquid and gas. And so the answer is that it's not spontaneous right now at that temperature and pressure. It's at equilibrium. And that's why if you manage to actually get the temperature of your water to be exactly 100 degrees Celsius, you wouldn't see it boil. You have to get it above, at least slightly above, to get it to boil. The next one is you just have to understand that entropy, delta S, increases as disorder, motion, heat, etc. increase. And so instead of the entropy of the system decreasing, instead it increases as the freedom of motion increases. And so the next one, I should make a point here because this relates to this next question. When I was saying delta S here, I was talking about for the system. But the delta S of the universe can never be negative. And this is a really important fact. if a process is at equilibrium, the delta S of the universe is 0. But all other processes that are spontaneous, the delta S of the universe is greater than 0. And so the entropy of the universe always increases no matter what's happening. And that's why some people, and it's definitely true that at some point it'll hit a maximum. And we won't have any more heat and no more reactions will happen. Everything will be at equilibrium. But this is not something to worry about. It'll happen far, far, far later than humanity will survive. And finally, G relates to this question, so I'm going to stay right here. Delta S of the universe increasing. What this really means is that energy is being more equally distributed. Heat, the main way that entropy increases is that heat goes from hot places, so H to C. That's how heat travels, and then these both sort of come to an equilibrium. And so heat is naturally dispersing, energy is naturally dispersing in spontaneous processes. So G is true. And our last one, so let's keep it here because it relates to it. I said that the delta S of the universe at equilibrium is equal to 0. And so we're discussing an equilibrium process here. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And yeah, they can both be 0, and delta S of the universe will equal 0 as it should, but they don't have to be. We could have, positive 3 and negative 3, and then the delta S of the universe will still equal 0. And so the question is, the statement is kind of true. The sum of these two equals 0, but they themselves don't have to equal 0, and that's the answer.